So, intermolecular bonding. This is within molecules, right? Intra is within the same molecule. Inter is other molecules having an interaction with you. There are 3 types. You guys didn't do this, right? This is new? Okay. So there's 3 types. There are London dispersion forces. Any guesses on the guy that discovered these? His last name? Yeah, that's his last name. His name was dispersion forces. Correct. These are the weakest. And they're always present. Every molecule has these. So London dispersion forces. Then there are dipole forces. These are for polar molecules. BW means between. And then within dipole forces, we create a separate category because they're the strongest of the 3. And this is a hydrogen bond. And I talked about that last week. We're going to go into more detail about that. So a hydrogen bond. It's a really strong type of dipole. Okay. Sometimes these forces, you'll see this name sometimes if you go on and you do some reading and stuff, are called, I'll rewrite that, van der Waals forces. I've seen everything kind of does it differently. Some people lump all these together, call them van der Waals forces. There's even, you can break down the London dispersion forces into a couple of subcategories, like just like we did with atomic theory. You can just keep breaking stuff down. But basically, there's London dispersion forces, there's dipole forces, hydrogen bonds, which are a type of dipole, or you can just say there's van der Waals forces, which are these intermolecular forces. Okay. Those are the 3 types we're going to talk about: London, dipole, and hydrogen. WAALF. I think it's AA. Now I'm questioning myself. All right. So just for clarity, an inter is between different molecules. Okay. Intra is within the same molecule. Which do you think is stronger? Or which is stronger? Intra or inter? Intra is the stronger one because it holds the bond together. Inter is in general the weaker one. They are not completely negligible. And I'll show you, hopefully tomorrow I can show a couple demonstrations that illustrate that point. But this is why, have you ever seen those little water strider things that walk on water? All right. They do that using the intermolecular forces of water holds the water as a flat surface, and because they're not heavy enough, they don't break through, and they can disperse their weight over their feet. We're going to do something like this maybe tomorrow, putting drops of water on a penny, and then if you change it from water to something else, you don't get as many drops, or you could get more drops depending on what you change it to, because the hydrogen bonding can create like a dome, all right, and hold it together without it falling apart. All right, and then I think I talked about DNA or mentioned it last week. DNA folds over because of hydrogen bonding, which tightens it up and it fits in your cell. Okay, because it actually would be around 3 meters long if you unwound it, but that's not going to work for your body, right? So they play big roles in things. All right, let's talk about what they are. My apologies, this is a lot of theory, kind of like the last chapter. Okay, London dispersion forces. These are temporary dipoles. Okay, so the electrons don't just sit there, right? Electrons are moving all around. So what happens is all of a sudden, all the electrons will be on one side of the atom as opposed to the other side. So they result from the random movement of electrons. So the electrons in this atom are just all equally distributed, but they're still moving. So in one instance, they might all be, most of them, not all of them, will be over to this side. When that happens, so we get I don't even like saying side because it's a three-dimensional thing, but that kind of makes sense. The electrons move to one side. When they do that, if there's more electrons here than there are here, you generate a partial negative charge. Okay? Now this happens like very, very fast. And when that happens, so now you've got this charge separation. So then the other atom beside it has electrons here, right? It's got electrons all nice and evenly distributed. But what happens is because of this positive charge, see, it's positive charge, these electrons start to feel a pull towards that. So then it's like a cascading effect. All right? So now this is still this charge separation. These electrons have been pulled this way, which creates a partial negative on this side. Now this is a partial positive. So now all these blue electrons are over here. And you've created what they call an induced. This dipole, so dipole just means a charge separation. This dipole was induced by this one. This one just happened randomly because of the electrons moving, but because it formed this charge separation, it pulled the electron density over. So now you created another one here. Then what do you think happens? And then this is going to create another one, which is going to create another one, which is going to create another one. So you start to generate this charge separation. Okay? This is all instantaneous. It happens and then it goes away. Then it happens and it goes away. Because the electrons are moving at the speed of light. Okay? So these are temporary, instantaneous. They occur and then disappear. And they are very, very weak. Okay? All right? Does that make sense? So they occur randomly, they occur instantaneously, and then they go away. But once they happen, they start a cascading effect within all the other atoms. So something that was not charged now has an induced charge on it. Okay? They are very weak though, okay? All molecules have them. They're usually overshadowed by other stronger forces. But these are really important for the noble gases and other nonpolar molecules because it's all they have. All right? So noble gases, Brinkelhoff gases, things like that. So neon, Br2, these have a difference in electronegativity of 0. Okay? But because of this effect, they do generate, this is the only charge that they can generate. They can't generate a polar charge because there's no charge separation. The size of the London force is dependent upon the size of the atom. The bigger the atom, the larger the London force. Because if you think about it, if the electron cloud is close to the nucleus, it's hard to pull it away. Like if you have candy here and you hold it really close, it's hard to pull that away. But if you have candy like this, it's easier to pull it away because they're further away from your body. Think of it that way, if that makes sense. I don't know if that makes sense. Okay? But the further the electron cloud is away from your body, the easier it is to start to shift it one way or the other. But if it's really close, it's hard to shift it. So the larger the atom, the larger the electron cloud, so that it's easier to distort the electron cloud, and you get stronger London forces. Oh, I feel like I've been talking too much. Let's. I don't really want to go on. We're just gonna stop there. I'm about to die anyway.